Writing a mathematical equation for ARIMA 111. One of the most widely used models for forecasting time series data is the ARIMA Auto-Regressive Integrated Moving Average Model. In this article, we will delve into the mathematical equation for the ARIMA model, incorporating the AR parameter phi, the MA parameter theta, and the constant parameter mu. Understanding ARIMA 111. The ARIMA model is characterized by three key components. AR autoregressive. This component captures the relationship between an observation and a number of lagged observations. I integrated. This component involves differencing the data to make it stationary, which is a requirement for the ARIMA model. MA moving average. This component models the relationship between an observation and a residual error from a moving average model applied to lagged observations. The notation ARIMA. P, D, Q refers to the parameters. P, the number of lag observations included in the model, AR part. D, the number of times that the raw observations are differenced, I part. Q, the size of the moving average window, MA part. For ARIMA 111 we have P equals 1, D equals 1, Q equals 1. The mathematical equation for ARIMA 111. The mathematical equation for the ARIMA 111 model can be expressed as follows. Where? Breakdown of the equation. First difference. The term delta YT represents the change in the time series value from one period to the next, which helps to stabilize the mean of the time series. Constant term mu. This component captures the average change in the time series, providing a baseline value around which the fluctuations occur. AR parameter, phi. The AR parameter phi reflects the influence of the previous period's change on the current change. If phi is positive, it indicates that an increase in the previous period's change leads to an increase in the current period's change. MA parameter theta. The MA parameter theta accounts for the influence of the previous period's error on the current change. A positive theta suggests that a positive error in the previous period will result in a positive change in the current period. Worked example. Let's consider a simple example to illustrate how to apply the ARIMA 111 model. Assume we have a time series data set representing monthly sales figures for a product. After applying differencing, we obtain the following values for delta YT. Assuming mu equals 3, phi equals 0.7, and theta equals 0.5, we can substitute these values into our equation. Delta y igual a 3 más 0.75 más 12 y 52 más 1. Calculating this gives delta y igual a 3 más 3.5 más 1 más 1 igual a 9.5. Thus, the predicted change in sales for the current month would be 9.5 units. In conclusion, the ARIMA 111 model is a powerful tool for time series forecasting, allowing analysts to capture both the autoregressive and moving average components of the data. By understanding the mathematical equation and its components, learners can effectively apply this model to their own data sets. For further reading, consider exploring these scholarly sources. Box GP and Jenkins GM. Time Series Analysis, Forecasting and Control. Hinman RJ and Athanasopoulos G. Forecasting, Principles and Practice.